So the plan for today is I'm going to go over the solutions of your first homework. If you have noticed, I already graded them and posted your grades on the news group. I'm going to go over the results of your first homework, and then we are going to finish line segment intersection. We haven't talked about the degeneracies in detail. And we are going to talk about the pseudocode of the algorithm, which computes, which takes care of all these degenerate cases. And then we are going to finish line segment intersection probably in the first hour. Then I'm going to talk about how to represent regions on a plane. So if we have a map, a two-dimensional possibly unbounded plane, how do we represent regions on this plane? And these regions we are going to be using, these regions are going to be bounded by linear, by line segments. So we are not going to have, not going to be talking about regions that have curved boundaries. If there are such regions with curved boundaries, such boundaries can always be approximated by short line segments. So at the end, we are going to see that we'll be able to represent regions on a plane, which we call such regions. These are called planar subdivisions. Okay, so if we have a plane, if we divide this plane into subregions, these are called planar subdivisions on the plane. How to represent such a planar subdivision? So it's like you have a map. For example, if you have a Turkey map, for example, the city boundaries in this Turkey map give you a planar subdivision of the Turkey map. Okay, we have regions that is occupied by a different city. We are going to see the city case is not very complicated. We can have more complicated planar subdivision in which there are holes within regions. For example, you may be considering a forest region, for example. There may be a lake in the middle of that forest region. So when you're going to represent the whole region as a forest, you cannot use a simple convex or concave shape, closed shape to represent that forest region. You also need to have a hole that represents the lake region. So lake region is another subdivision, which is also part of this one. So some regions may have holes in them, and in general, the number of holes may be more than one. You may have a face which consists of many holes in it. So how to represent such planar subdivisions is going to be the main topic of today's lecture. We are going to introduce a data structure called the doubly connected edge list to represent the doubly connected edge list. Actually, it's all edge list, and it's also it contains a vertex list and a face list. We are going to talk about this data structure. And we are going to use this data structure to compute the overlay of two different subdivisions. For example, one subdivision may be the natural, these like forests, lakes, so the different natural vegetation areas, okay? For example, farms or the different fields you can have. So one of them may be the vegetation map of Turkey, which is represented by a specific, by a certain subdivision. And the other subdivision may be the city subdivision. So we may need to overlay these two to find, for example, which city has the largest forest area, for example. To be able to find this, what you need to do is you need to overlay these two subdivisions to create a new subdivision which consists of information from both subdivisions. So this is called the map overlay problem. It's not called, we are not intersecting or taking the union of subdivisions. So it's not an intersection or union problem. It's a different problem, actually. We are creating a new subdivision which contains both information. So it's like integrating two subdivisions, and this therefore is called its overlay of two subdivisions. And when I give you an example, it's going to become more clear about what the operation we are doing does not necessarily mean intersection or union or difference. Okay, so today's main topic will be the map overlay problem after we finish the line segment intersection. Okay, so let's talk about the homework now. So I graded the homeworks, and as you may have seen, most of you got full grades, 100 from the homework. And there are a couple of like 80s, 90s, 85, 90. Those students lost points from the last, most of them lost from the last, the C part, the last part of the homework, which states, which needs you to show that it has an if and only if part, okay? So you need to show both sides of the proof. You need to show if this happens, then this happens. And you need to also show if this happens, then this happens. If you have an if and only if in that statement, you have to prove both sides. So some of you lost like 10 or 15 points from that part. And also there are two very low grades, like around 30. And these are the ones which use the solution that is found on the internet. Okay, so I didn't know there was the solution of this homework on the internet, but I found it at Rutgers University. There is a computational geometry course as well, so their first homework was also solving the same set of problems. So what I want you to do is I want you to try to even, I mean, some of the proofs who got 100, I mean, they're very simple proofs. Actually, if I graded those in full detail, maybe they may not be complete proofs, okay? But the thing is, I mean, you think about the solution yourself and try to, if you try to attack the problem yourself, you find something, you can say something about by using induction. Or I also seen different solutions, some of them proof by induction and proof by construction. And proof by contradiction for other things. So you can actually try to attack the problem, even if your proof is not 100% correct, if you have something meaningful. I mean, it's not, what I did was I gave you full credit if it's not even, there are some small loops in your proof. So my goal in these assignments is that just to think about the geometry and the computational aspects of the problem yourselves, okay? So, I mean, maybe I didn't actually, when I first gave the homework, I didn't explicitly state that you cannot use other sources. I mean, maybe I should have said that, but I also have the freedom of grading however I like, okay? So, I mean, if I say, okay, I don't like your solution because it doesn't seem like your solution, okay? So, so this is why I cut points of these homeworks. And actually, the solution in Rutgers University is an excellent solution. It's a very nice proof. Okay, it's very short and it looks at the problem and very different. It's not proof by induction, but it's a nice proof. But you can solve for example, the first problem, if you remember, was the convex hull of a set of unit circles is composed of circle arcs and line segments, straight line segments. So prove that it's the case. And one solution was a really smart solution. I mean, the statement actually is incorrect for a circle of, if n is equal to, I mean, if you assume in the exercise, it doesn't state that n is greater or equal to 2, okay? It just say n, okay? And for n is equal to 1, this statement is actually false, okay? Because it is not composed of arcs and line, and we should take this and as a strict and. It's not composed of circle arcs and line segments for a circle of, for one circle. For one circle, the convex hull is the circle itself, so there are no line segments, so the statement is false. So this is how you prove the opposite, and that's it. Okay. So, I mean, if you don't want to tackle with the real problem, I mean, I had to give full credit to him for this, because the question was not fully stated. So it's just n greater than equal to 2. So the proof for n is greater than equal to 2, again, the statement is true for n is greater than or equal to 2. If we have, and most of you did proof by induction, which is correct. And some of you use, I mean, and all of these proofs, the common point was you were using tangents to circles. Some of the proofs did not use tangents to circles, but what they did was they combined. So, okay, the proof by induction is like this. First, you show this is true for 2 circles. So your base case is n is equal to 2. Given 2 circles, your convex solve. I mean, these 2 circles may also be overlapping. Okay, I mean, they may be intersecting like this. Even at this intersection, the convex solve, what you use is you use the common tangents. There are here okay, so these are the common tangents of these circles. There are also 2 other more common tangents. Yeah, these. So these are also common tangents. But we are interested in the common tangents in which both circles are on the same side of this tangent. So it gives us 2 such tangents, and we see that. So there are 2 different properties of a convex solve. It's the minimal convex. So that's minimality property is used in many proofs. So it's, for example, in one proof which constructed a convex polygon by treating this like by using these common tangents, and each of these common tangents, if all the circles, I mean, this is another proof, not the base case. Okay, just think about another proof which consists of looking at all the circles and looking at common tangents of these circles, in which all the other circles lie to one side of this tangent. So this defines a half plane, this such tangent, and the intersection of all such tangents in which all the other circles lies in the other place gives you a convex polygon. Okay, and they first show this convex polygon, which is just composed of line segments, and because of the minimality property of this, they looked at, for example, these common tangents. Usually when they create the convex polygon around circles, it becomes something like this, but the minimality convex, they erase these parts, and then that showed, I mean, this one also showed that, I mean, it's composed of these line segments, and these, if you take these erased parts out, you get arcs of circles. So it's one way to prove it. It may,
so this is proof by construction?
Yeah, it's maybe called proof by construction. It's, but you're constructing a convex solve using this algorithm. So it describes an algorithm to construct a convex solve. So this is an algorithm to construct a convex solve, and this algorithm creates certain, in that part of the algorithm, you delete certain regions, and this deletion leaves you with certain circle arcs. And the induction, so after you show the base case, the induction, the hypothesis is, I mean, if it is true for n-1 or n circles, I mean, it's what is true. Our hypothesis is for n-1 circles, if our convex solve is consisting of line segments and circle arcs, if I put the new one here, it is also going to introduce line segments and arcs into the convex solve only. So, and what you do is you use tangents. This time these tangents may come from 2 different circles already in the convex solve, and at the end again you see what you introduce in the convex hull is a circle arc and line segments, which completes the proof. But let me tell you the solution in Rutgers University. What it says is that consider the convex hull of unit circles. Now, it proves this with the use of extreme points of this convex hull. So what's an extreme point of a convex hull? A line segment is not going to be an extreme point is a point which is like if you think about it as so in which if you drove a certain tangent, this point, the tangent point, compared to the neighborhood, this point is an extreme point. It's the highest point because all of the look at this curve around this point. All the points are at a smaller height than this point based on this tangent. So this point becomes an extreme point on the circle. But for a single circle arc, there are infinitely many extreme points. Okay, this one is also an extreme point, for example, for this tangent. Okay, I mean, and even for a circle arc that is part of a convex hull, there are infinitely many extreme points here. But what the proof says is that an extreme point belongs to if you look at all the extreme points in this convex hull, you see that they can only be part of circle arcs. Okay, I mean, if you look at a segment, the tangent to this segment, there is no single extreme point. All the points next to it are also on at the same level. So we cannot talk about extreme points as circle. So, what they say is that in that proof, let me read. It's a very short proof, like 3 sentences. Okay, the part A. It says. If we consider all possible lines such that no part of the convex hull is on its left side, and if we consider lines such that the intersection of this line and the convex hull is not an empty set. So consider lines that touch the convex hull, but all the convex hull is to one side of this line. Okay, so we consider such lines that touch the convex hull, but all the convex hull lies to one side of this line. So there are 2 cases when such a line touches. One is when it touches a circle arc, and the other when it touches the linear part of the convex hull. So if the proposition was our convex hull was composed of circle arcs and line segments, if there are such lines that touch the convex hull, they can either touch the circle arcs or the line segments. So in the first case, if actually the proof does not even assume that these are circle arcs or line segments. So the 2 cases are explained like this. If you look at there are these 2 cases, the line can touch either at a single point, this line can touch the convex hull at a single point P, or it contains the intersection of this line and the convex hull contains many points. So if it's a single point, then it should be on the boundary of some circle, since this intersection is an extreme point. And this, what is going to happen is that since we are touching, this at P, we are also going to look at all the neighbors of P, and we are going to show that we see that it is part of a circle. And in the case that the touching line to the convex hull contains many points, it must be a common tangent line of 2 circles. So this proof also used the concept of common tangent line. So if we are touching this convex hull at infinitely many points, then it must be the common tangent of 2 circles. And this line segment between these two tangent points is on the convex hull. And in this case, yeah, and then this also shows there are these two cases show you that it can only be composed of circle arcs and line segments. Now, if we come to the part B, the fact that a single circle contribute to one one point or one arc on the convex hull. So let's look at the statement in detail. Okay, here. Show that each circle can occur at most once on the boundary of the convex hull. Okay, so there is also an easy way to prove this. This statement is wrong. Okay, if you have three circles, so the statement says that the circle can occur at most once. So this occurrence is not defined very clearly. I mean, this statement does not say that a circle contributes at most one arc on the convex hull. You may show as such a case, the circle occurs on the convex hull as a point. Okay, so in the case of three circles, which are parallel to each, which are on the same line, this middle circle here occurs. I mean, it actually, you may say it occurs on the convex hull at these 2 points. So at 2 different points it occurs, so the statement is false. Again, you may prove it like that, but if the statement says that if a circle cannot contribute more than 2 arcs, then you can again use the same picture actually to prove this. In order for the circle to contribute an arc here and an arc here, we need to have tangent lines which leaves a certain portion of the circle arc open. I mean, since this part is the convex hull, we need to have lines like this, and such a case can only occur, and we need to have arcs like these as well. I mean, such a case can only occur if these 2 circles are smaller than unit circles. Okay, if they are unit circles, such tangent lines cannot occur, and since all we have is unit circles, we cannot have such a circle contributing twice as arcs on the convex hull. There are other ways to prove this as well. I mean, in general, you did really good in this homework. I mean, I thought this was a difficult homework at first, but almost everybody, I mean, have provided good answers. So if you think about the problem, the solutions may not be as difficult as it seems at first. And the last part was to show that if we consider the convex hull of the center points of these circles, a center point is on the convex hull of this center point convex hulls if and only if its circle contributes an arc to the original convex hull of circles. So again, this can be proven by considering a line, I mean by shrinking the original convex hull by the radius or the unit amount until you reach the convex points. And most of the proofs are proof by contradiction, which shows that during this contraction of the convex hull to the center point convex hull, another circle cannot appear as arc because each of them are unit circles. If a circle can, again, you need to prove this both 2 ways. I mean, if this is you need to both have the shrinkage part and expansion part, okay? But starting from the convex hull of centers, you need to grow it into circles and see that no other circle can appear during this expansion. And this follows from the observation that all of them are unit circles. No other circle will be able to appear during this expansion or contraction. Okay, so this was the homework in general, and you can look at your papers during the break if you want to see where you lost your points. Are there any questions about the homework? Okay, so let's continue with line segment intersection. Now, I'm going to draw something, this figure is from your book, which shows several degenerate cases at one figure, at one instance. And we are generally interested in degenerate cases in which an intersection is shared between multiple line segments. And for example, there may be more than two lines ending at the same endpoint, or there may be more than one line ending at the same vertex or point, or there may be more than one line segment that starts at the same point. So I'm going to draw a figure which has multiple segments starting at the same. So we are going to have an event point, which is a very complex event point. Some line segments are going to have this event point in their interior. Some of them are going to have them in their ending points, and some of them are going to have it in their starting endpoints. And we are going to see what happens to our study structure at the before and after this event point, and how we handle intersections and do not miss any intersections. So this figure is a very complex figure. I hope I'll be able to draw it according to the book. It has 8 line segments. Okay, it has 8 line segments, 2 of which are not related to this event point. So we have, let's use the same convention. So S7 and S8 are the 2 line segments that are not related with this event, but they will be, during event handling, we'll be able to we'll have to look at these lines during event handling. So we have, let me use this. So this is our sweep line. Okay, so this is our line L, is the sweep line, and we have an event point here on this sweep line, and one segment S5 is ending at this event point. One segment S3 let me write it here. So this is also S3. Has this event point in its interior, so it intersects here. And another one also, I mean S1 and S3, both of them have this event point in their interior, meaning that they intersect. S1 and S3 intersect at this event point. And let's have another S4 ending at the same event point, and S2 starting at this event point. Okay, so I have S1, S2, S3, S4, S5. Where's S6? So I also have, they don't have S6 in the, let's see. So they don't like the number 6, so they didn't give it to any segment label. That's interesting. Maybe we can have another second segment starting here, okay? Let's name it. But is it going to change? Yeah, let's forget about it for now. But we can edit later to see what will happen. Okay, yes. All right. Now, just before the, now I'm going to show the study structure just before this event. when the sweep line is just slightly above this sweep line L, and what will happen when it is after the event point, this event point P. Let's name it as P. Okay. So before this event point, our study structure, the leaves of our study structure should show that S7 should show this order: S7, S5, S4, S1, S3, and S8. So we should have a tree on which, on its leaves, we are going to see this order of segments. Let me write it here: S7, S5, S4, S1, S3, S8. We don't have S2 yet. Before S2 is added at this point. We don't, before the sweep line, we don't have S2. Okay, we have S7, S5, S4, 1, 3, and 8. So these are the segments before we encounter this event point P, and they should be added. These segments have to be added to the study structure at some point, at an earlier intersection point or at an earlier event point. For example, if you just look at this picture here, the last event point before this seems as 5. Okay, S5. If these are all the line segments in our line segment list, probably S5. S5 was the, not probably, it's for certain. S5 is the last event point before P. So just after S5, our study structure should reflect this order on the study structure tree. And our tree, since we have a balanced binary tree, we need to make sure we are using a balanced binary search tree to store these segments. Otherwise, we're not going to guarantee log n insertion and log n deletion time. And here is one such, yes?
Burada bu sorting neye göre oluyor? X koordinatın değerine göre oluyor değil mi?
The question is, so how do we sort these things? Okay, these are line segments. These are not just points. So the sorting, as the book says, the sorting indicates the order of these line segments as they intersect according to their intersection of the sweep line from left to right. Okay? So it shows that since these are line segments, this order is not unique for a given set of line segments. We need a sweep line. Where are we on the sweep line? Which sweep line intersects these line segments? So this order, for example, S1 look at S1 and S3. Above the sweep line, S1 is to the left of S3, but below the sweep line, S1 is to the right of S3. So their order is dynamic. At this event point, we need to make sure that S1 and S3 change their orders. So we do not actually, by just looking at the line segments alone, we cannot order them. The proper order between them, which one is greater than other, is determined according to a given sweep line. Okay, according to, now here, when we come to an event point, actually at this event point P, just exactly on that event point P, actually all of them here, they intersect, the sweep line, the ones other than S7 and S8, all the other ones, these S5, 4, 1, and 3, they intersect the sweep line at the same point. Okay, so they are equal in terms of their order. Okay, at this event point P, you cannot say S3 is greater than S1 or S1 is greater than S3. They are equal. They intersect the event line, sweep line at the same point. So how are we going to order them? So if we do this order based on this point P, we'll be able to come to the conclusion that S1 is equal to S3 We cannot say which one of them is greater than the other. So what we do is we order them according to how they will appear, just tiny bit lower from this event point P. In other words, what we wonder is that since we say that between this event point P and the next event point, so if this is Pi for example, and the next event point will be Pi plus 1, it is here. We know that between these two event points, nothing will change. So the order of the segments, or we are not going to encounter any endpoint, intersection point, nothing. So we sweep the whole plane by using these discrete event points. Our main assumption is that nothing changes between these two event points. If something changes, here for example, this must be our event point. Okay, I mean the places where things change in the study structure are the places which are called event points. Okay, so by definition, between Pi plus 1 and Pi, our study structure does not change. So what happens is that you take any line here, this one, or this one, or this one, the order of the line segments does not change. So you can order the line segments based on an imaginary line between Pi and Pi plus 1. Actually what you can do is, since you know Pi, the place of Pi, you know Pi plus 1, you can, to be robust for example, you can create a temporary sweep line which is equal to Pi plus 1 divided by 2. Okay, and there its y coordinate may be something in the middle, and just compute, at this point, compute the order of these line segments according to their intersection of this imaginary sweep line.
Ya bunun Pi plus 1 ile Pi minus 1 olması gerekmiyor. Çünkü bir alttaki imaginary sweep line güçleri olursa S2 gibi yeni bir line karşımıza çıkıyor.
I mean, this I and I plus 1 are just indices. It means, I mean, we are moving from top to bottom. Our sweep line goes like this. And I and I plus 1 does not say anything about their y coordinates. I mean, Pi plus 1's y coordinate is actually lower than Pi. Why did you object to I plus 1 here?
Yani sweep line biraz daha aşağı çekmek yerine biraz daha yukarı çekmek şeklinde kullanılması gerekiyor.
Oh, no. Oh, I see. What you say is that the order at this point should indicate the order here, you mean?
Yani bu sweep line'ı biraz daha aşağı çektiğimiz zaman yeni bir event point eklenmediği için buradaki ortada bir şeyin değişmediğini söylediniz. Ama biraz daha aşağı çektiğimiz zaman S4 line'ı ortadan kayboluyor. S4 line çünkü
yes.
Yeni sweep line'la intersect etmiyor. Bu tarafta
Exactly.
S2
because yeah, that's exactly the case. At this point, S4 is not going to be on the study structure. At this point, you need to remove it from the study structure.
Ama bu ordering biz buna göre yapacaksak yani yukarı çekip
I mean, we are not thinking about this order right now. We are at that event point P. The order, this was the order before event point P, Pi. At event point Pi, the order is going to be S7, S3, S2, S1, and S8. Okay? So this is how the study structure changes at event point P. At event point P, your study structure should be like that. Okay? So in order to be able to achieve that order, you need to consider just what will happen just a tiny bit below, or I mean, you don't need to think about it. You may say, how do I define tiny bit below the sweep line? Don't worry about it. It doesn't need to be tiny bit below. It can be halfway between the next event point and this event point. Because you know, during all this region between Pi and Pi plus 1, this order, S7, 3, 2, 1, 8, does not change. And this is this is the order we are looking for. Okay, so when we are actually implementing this binary search tree, we need to maybe send both of these event points, I mean this event point's y coordinate and this event point's y coordinate should be sent to this comparator function which compares two line segments. It becomes, I mean, all we need in order to create such an order, such a binary search tree, we can use existing like AVL trees and even the implementation of hash set in Java, for example, use, I guess, a balanced binary search tree. Hash set and other, the tree in STL library of C++, I think it's also use a balanced binary search tree. It's either a red-black tree or an AVL tree. But in order to use such an existing library of a binary search tree, all we need to do is to define how do we compare two objects, okay? We are going to store objects in this tree, and how you need to provide a comparator function, I mean, these objects should implement the comparator interface, and you need to be able to compare two segments based on, because when you're putting them in this tree, you are going to be asking questions. This intermediate node, is it greater or less than the current node I'm trying to insert? So we are going to be asking this, we are going to be doing this comparison during insertion. So we need to add this comparator function, and what I'm trying to say is that this comparator function, if for example, you are going to compare two things, S1 and S3. You are going to compare S1 and S3. Just sending these two line segments with their two endpoints is not enough for the comparator function to define which one is greater than the other. What we can do is we can add, assuming that we are doing a horizontal sweep from top to bottom, we can also send to this function, this comparator function, two y coordinates, okay? Y coord I and y coord I plus 1. So we can send the y coordinates of the current event point and the next event point. And in order to find which one is to the left or other, all we need to do is we need to intersect these S1 at y is equal to, for example, this plus this divided by 2. Okay? I mean, this is just a halfway between these two event points. I'm trying to define practically how to define this tiny bit below the event point. So it can be the halfway between these two event points, because you know nothing is going to change. So all you need to do to determine whether S1 is going to be greater than S3 or S3 is going to be greater than S1, all you need to do is intersect these two line segments at y is equal to this. How do you do that? Again, you can, since you know y is equal to this, you also have this for each line segments, you can have this parametric line equation. At this y, these are known. All you need to do is find u. After you find u, you put it into its x function, and you find an x for one line segment. You find another x for the other line segment. Your comparator function becomes the comparison of two floating point numbers. Compare these two x's. If x1 is smaller than x3, return whether x1 is smaller than x3. This is your comparator function becomes as simple as this. Okay, because the x coordinate that you are going to compute is going to give you where they intersect the sweep line, that imaginary sweep line. So you need to, I mean, these are very low-level implementation details, but if you think about implementing this line segment intersection algorithm, you really need to consider such low-level details in order to have a correctly running algorithm. Okay, so is everything clear? Any point unclear? Just ask. Yes?
How can we use the ordering of these segments, 5x4, x1, etc.?
The first one, this one.
To the other one.
So how are we going to make this change? Okay, very good. In order to make this change, what we need to do is, at this event point P, since the tree is already, the objects are already in the tree, their orders, it means their orders are fixed. So what we need to do is, first of all, we know that the segments whose lower endpoints are at this event point should be removed from the tree, such as S4, right? So you are going to look at, and we know that at this event point, such segments are stored with the event point. When we insert the event point, we say that we have links to these segments. Mm-hmm. Yeah, I'm going to come to that. Yeah, I mean, you mean? Mm-hmm. Yeah, actually we have other not ending, for example, S1 and S3. Yeah, there can be 3, it doesn't matter. So we can have S5. Okay, let's assume S5 goes like this as well. Now, we removed S4 from the list. Now, what we do is, for those segments who are intersecting at this point, what we are going to do is, we are going to first remove all of them from the tree. We are going to remove them, and we are going to reinsert them. And during this reinsertion, we are going to be using the new we are going to compare them according to this P. Okay? So when you are if you remove them, at this, I mean, consider this function again. Okay? We are going to compare S1 with S3, S1 with S5, S5 with S3. Now, according to the new y coordinates, the new sweep line, they are going to be compared according to the new, according to this pivot point P. Yes, they're equal at that point, but they're not equal at a point here. They're equal at point P. Yeah, this was what I was trying to say. At this point P, there is no way to order them because they all intersect at the same point. They're equal. But if we consider this L, consider the line L plus epsilon, what will their order then? This comparator function, this is your goal. You try to compute what is their order going to be at L plus epsilon. And what I'm trying to say is, their order at L plus epsilon is the same as their order at pi plus 1 divided by 2. I mean, at the epsilon lower than the sweep line, or you're halfway in between 2 event points, their order do not change. Ordering of S1, S3, S5. Mm-hmm. No, it can be done in constant time. This ordering is a simple, what you are doing is, it's a constant operation. It doesn't add to the asymptotic complexity of the algorithm, because this function that I'm writing here, it takes all one time. Mm-hmm. Oh, okay. All of the lines which are going to change order. That's a good question. The question is, what happens? I mean, the lines that we are going to remove and reinsert again, does this add to the complexity? Because to compute the reordering of the lines, all we need to do is, for those lines that have this point as their interior, all we need to do is remove them and reinsert to the tree again. And all this reinsertion, the removing takes log n time for all these lines, and inserting also takes log n time because these are binary search trees. So it turns out that since we are going to actually when proving the complexity of this algorithm we are going to take into the consideration, and it turns out that this because of this log n addition and log n insertion time, it doesn't add to the complexity more than log n for each line. So at the end, it doesn't increase the n log n overall complexity of the algorithm. What you may be thinking is that each line, if every point, if I insert and delete every line, what happens? So it's like maybe if you need to, so it seems like can n square log n, it increases to n square log n maybe, because if at each event point, if you insert, if you remove and insert all n lines, it's like n log n information at each event point. Since we have n of such event points, it's going to be n square log n at the end, but we need to show that the number of intersecting points, I mean these lines, the same line is not, I mean we need to show that at each event point we are not going to consider n lines. Here we are going to be, the total is going to be bounded by the number of intersections. Okay, it can be n square log n only if you have n square intersections. Okay, so the final complexity becomes again an output sensitive algorithm. N log n plus I log n, which I is equal to the order of intersections. If you have n square intersections, then you can have n square log n complexity. Okay, so this is bounded by the number of intersections. But very good question. Now, so we almost described the algorithm. At an event point, what we are going to do is, for those segments which have this point P as their lower end points, we are going to remove them from the tree. And for those ones which have them in their interior, we are going to first remove them from the tree and then reinsert them. And for those segments that are starting, like S2 is starting at this event point P, they are going to be also inserted into the tree at that point. And during this, after this insertion deletion, we are not done yet. What changes that? All the neighborhood information, remember, we were using a lemma which states that if two line segments intersect, they become neighbors at a certain event point. So we need to, since for example S5 was very far away from S8 before this event point, now S5 is a neighbor of S8. So we need to check this right neighbor and this left neighbor segments are important because we'll need to, after this reordering of these nodes that are associated with this event point, we need to be able to find the rightmost segment in this new order and the leftmost segment in this new order and check whether S7 and S3 intersect, or S5 and S8 intersect. If they intersect, for example, they could have been like this. This is the point they become neighbor. This intersection is detected at this event point. Okay? And as soon as we detect this intersection, this also becomes what? An event point. Okay, when we detect this intersection, this becomes event point because then S5 and S8 change their order. S5 may become neighbors to another one. Here, for example, S9.
Peki mesela S7 ve S3 için hani orada hemen altında P'nin.
They are become neighbors as well. Yes, we just check. It's not guaranteed. Being neighbor does not guarantee intersection. All we need to do is, when they become neighbor, we need to check whether they intersect or not. That's the line segment intersection test between two line segments. Okay, so the checking of line segment intersection, we know it's we treat it as a it's a primitive geometric operation. Given two line segments, whether they intersect or not. You remember we were looking cross products, two sides, and then using the parametric line equation to find the intersection point.
We do not improve the efficiency of this primitive.
No, we just say that it's the constant time. It's the constant time O1 time operation to check between two line segments whether they intersect or not. I mean, the book even does not even talk about how we do this check. It's just a check whether they intersect or not. Okay, so it's treated something as a primitive operation. So if they do not intersect, an event point is not inserted, and an intersection is not reported, and so on. So let's have a break, and during the break I'm going to write the pseudocode.